Okay, Physics 11H crew. I'm going to make you a quick video on Coulombs Law. Coulombs Law. And the force of attraction between charged particles. So you did the lab. You all did a very nice job on that. Most of you figured out that when you change the radius, that the force gets weaker or stronger, which is very much like the force of gravity. Fg equals big G m1 m2 over r squared, where, m1 is the mass of the two particles, r is the distance between their centers, right? That's r. And then Fg is the magnitude of the attractive force. And they both experience the same force. It is the same force. It's an attractive force. Acts to pull them together, the equal and opposite force. In fact, the force on M1 is coming from, I'll call this M2. The force on M2 is from object 1. Fg, we'd say, on M2 by M1. This is on M1 by M2, Newton's third law, equal and opposite direction. All right, equal magnitude, opposite direction. All right, so in general, that's the format of the force. Now, for electric force, the simulation, you may have noted that looked a lot like that force of gravity one with the two little stick figures pulling on it. Looked very similar, right? And it behaves very much like the force of gravity. But the big thing is with electric charge, you have positive and negative. We don't have positive and negative mass. There's no repulsion of mass that we know of or theorize exists. But we do have repulsion of charged objects, and I shouldn't say mass, of objects that have mass. We do have repulsion of objects that have charge when there's charge similarly. So let me just give you the equation for Hooke's law. We say Fe, so it's electric force. The constant in front of it now is quite a bit different. It's called the electrostatic constant, which is lowercase k. My note sheet goes through and shows for this unit, where is it? Epsilon and this and that. Just ignore that. We use the electrostatic constant. I'll show you what that is in a second. And then for charge, the symbol we use is a lowercase q. Q1 and Q2. All right? A lowercase q, and divided by the distance squared. It's the same exact format as gravitational force, and that's not by chance. It's a property, fundamental property of matter is charge and mass, right? So as you change the charge, it affects the force situation proportionally, just like it does with gravity. If you change the distance between the objects, it affects the force just like gravity. Fundamental property of matter. Pretty cool. So our drawing looks exactly the same. Q1, though, we'd say Q1 and Q2 and the radius between them. But the key here is the force now, the electric force acting between them, could be positive, or it could be, or I should say it should be attractive, can be attractive or repulsive, right? So that's the trick here, and that depends on what the sign on these charges are. We don't put the sign of the charge in this calculation. We simply put in the magnitude of the charge or the value of the charge into here, and then based on whether or not it's a positive and a positive, a negative and a negative, or a negative and a positive, or positive and negative, whatever, then we decide whether or not it's attractive or repulsive. All right, so K, all right. Well, actually, let's start off with Q. The units for Q that we have to use in this formula, that we typically use in this formula, are unit of charge, coulombs. coulombs, which is capital C. All right. One electron or proton has a charge of 1.6 times 10 to the minus 19th coulombs. Negative. One proton is positive 1.6 times 10 to the minus 19th coulombs. All right, so I got that glare going on here. So the proton and electron have the same charge, opposite sign. So charged objects, so if you have 1 coulomb of charge, you have, oh man, like a billion times a billion electrons or protons accumulated somewhere. So it's named after Coulomb. And that's pretty much it. It's a scientific base unit. It's one of the base units of science to go right along with meters, seconds. So we haven't seen a new base unit in quite a long time, if at all, this whole year. But it's a base unit. We don't break it down any further than just coulombs. These are 1 E, you know, that is a unit of charge. 1 E, that's the other unit of charge, fundamental charge units. That just assigns each electron to have a value of 1 or negative 1, and each proton to have a value of 1 positive 1. So 1 E is 1.6 times 10 to the minus 19th coulombs, and sometimes we have to convert between the two, but most of the time we just use units of coulombs to do the actual calculation. And the reason is because we typically deal with more than 1 electron at a time, or more than one. In fact, we typically deal with trillions of electrons and protons attracting and repelling all at one time, big charged objects. Getting text messages from my brother-in-law. I should put this on do not disturb. But anyway, so K is called the electrostatic constant. Lowercase k it is here. It's the electro constant. All right, electrostatic constant. Its value is 9 times 10 to the negative 9th, 99. And the units are funny. It's just newtons times meter squared per coulomb squared, right? So when K goes in here, coulombs on the bottom will cancel out with coulomb squared will cancel out with these two multiplied, and meter squared on top will cancel out with that. So whenever I give you a problem, you're going to have to make sure you're in coulombs and meters. All right, so let's just quick look at a little example. Let me just go over, I should have pulled this out and been ready for this video, but I got to find your packet that I gave you here. Oh boy. Oh boy, I'm ruffling through the papers. Where are they? Where are they? FG. La, 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 la. Come on, where are you? Rotation orbits, oscillations. Here we go. What's this? There we go. Found it. All right. I was looking at it digitally the other day. These are the master copies that I copied for you. This, I might come back to the conductors and insulators and look at it conceptually. This is really hard to do without the actual demonstrations and labs. They were a lot of fun. If God willing, if we make it back to school by the end of the year, if we do, I'll show you some of that. Anyhow, okay, here we go. Worksheet 1. I think I did not assign you problems 1 and 2. Let me go back and check that in the grade book. I think I assigned you numbers. Let's see. Sorry, guys. I'm ill prepared here. I think I assigned you... Yeah. Yeah, 4 and 5. Okay, good. I'm glad I didn't assign you 1 and 2. How many excess electrons do you need in some location to have a static charge of 1 coulomb? You just invert this. It ends up being a huge number. And typically deal with amounts of charge in the nanocoulomb or microcoulomb range. All right, that is important. These types of questions. Let me just explain that to you really quick. Typically, when we're doing these problems, we are in the nanocoulomb or microcoulomb range. All right. Turns out a microcoulomb of charge is actually quite a bit of charge. In fact, when we charge up the Van de Graaff generator school, which you guys haven't really seen, it accumulates picocoulombs of charge. So anyways, 1 NC nanocoulomb, that is 1 times 10 to the negative 9th coulombs. 1 microcoulomb is 1 times 10 to the negative 6 coulombs. All right. So if I say it's a microcoulomb or nanocoulomb, when you plug it into the electrostatic force law, Coulombs law, you have to put in this prefix, or not prefix, the scientific notation power there. All right. So anyway, I'm gonna skip over number 2. You can take a look at that. I'm gonna do number 3 for you. All right, right now, and then I'm gonna wrap this video off. All right. So number 3, I go through now the derivation of this equation. Like I said, when I pass these out, it's kind of interesting is we go into quarantine and my packets are starting to get annotated. I had built in a lot of notes to these packets as I made them, which ends up being good in this situation, right? For whatever reason, I had done it that way when I made these. Usually at this time of the year, what happens is I'm trying to move through the material quickly, so I want to make sure you guys have some notes to reference right on the packets. Yeah, you can order that 1/4 pi epsilon knot stuff. That is important later on in your physics life, but not for now. So the number 3 is an awesome problem. All right, number 3 is an awesome problem, and if you've watched this far, if you email me. Don't tell anybody about this. If you email me and say, hey, comma, I saw the bonus part, I will give you a bonus point on an assignment in case you need it. Okay? So anyway, this is a really important problem right here. Please watch on. It's really pretty cool. 2 objects with a mass of 1 gram. So look, I'm giving you the mass and the charge. So the mass of this object is 1 gram. You may remember is 0.001 kilograms. M2 is 0.001 kilograms. And a charge of positive 1 microcoulomb. So Q plus 1 times 10 to the negative 6 coulombs. Q2 plus 1 times 10 to the minus 6 coulombs. All right? Determine the force of electrostatic attraction between the 2 objects. And then over on part B, we're going to determine the force of gravitational attraction and then try to draw them to scale. So the distance separating these 2 centers is 3 centimeters R, which is 0.03 meters. All right, so remember, there's 100 centimeters in 1 meter, right? So we're looking at 3 centimeters. So I have to move this over, decimal place over a couple spots, 0.03 meters. 30 centimeters would be 0.30 meters. 300 centimeters would be 3.0 meters. All right, so don't forget how to convert. So let's figure out the electrostatic force. Fe equals K Q1 Q2 over R squared. My Q's are looking like A's, but you know, I'm running out of space. So let's plug everything in. Remember, K, 9 times 10 to the negative 9th. Wait. I'm sorry, not negative. Positive 9, 99. 10 to the negative 9th. Got brain fart there for a second. Sorry about that. newtons times meters squared per coulomb squared times 1 times 10 to the negative 6 coulombs. Now I could just square it because they're the same, but I'm not gonna. 1 times 10 to the negative 6. Notice I'm not putting the sign on these two charges. I'm just putting them in there like this. Divided by the distance between the center squared, 0.03 meters squared. Now we gotta hack this all into the calculator. All right, of course, my calculator is missing children. All right, I'm gonna pause this video quick and go upstairs and grab a calculator. Okay, back at it. 99 times 1 times 10 to the minus 6. So I like using this E notation. I don't know if you can see that. It's kind of... Don't forget to square the bottom. That's one of those classic mistakes. So this is what it looks like typed into my calculator. If you can, let me try to... Let me take the focus lock off for a second here. All right, this is what it looks like typed in my calculator. And enter. Oh, look at that. 10. Nice number. Goes 10 newtons. Beautiful. All right, let me put the focus lock back on. All right. Very nice. Very nice number. 10 newtons. Let me write it over here. Fe equals 10 newtons. Now, let's figure out Fg. So it's very similar equation. Calculation, very similar. Fg equals big G, M1, M2 over R squared. All right. Big G, 6.67 times 10 to the negative 11th. All right, so this is really small. Electrostatic constant is really big. Gravitational constant is really small. This is the scaling factor, right? This is what, this has to do with the field. It has to do with space with the field, how it penetrates space. So gravitational field is fairly weak as compared to the electrostatic field, or you can kind of say either way, the force or the field. Now the mass, 0.001. All right, so this mass is quite a bit bigger in terms of how, its size compared to the charge, it seems. But you'll see here, you'll see when we plug this all into our calculator, this ends up being pretty darn small. So 6.67 E minus 11 times 0.001 times 0.001 divided by 0.03 squared ends up being 7.4 times 10 to the negative 14th. The force of gravity acting between them. So the force of gravity acting between them is 7.4 times 10 to the negative 14th newtons. All right, very cool. So that's pretty darn weak, and hopefully I calculated that right. But anyhow, let's see. Let me just double 6.001.03 squared. Okay. Yep, looks like I did it right. Negative 14th newtons. Now, if we were to try to draw this to scale, right? Now, 10 newtons. Let's make 1 centimeter for each newton of force. So approximately 10 centimeters. Approximately 10 centimeters. That's the electrostatic force. All right, so I got to make this line 7.4 times 10 to the negative 14th centimeters. So 1 centimeter equals 1 newton, let's say. So I got to make it 7.4 times 10 to the negative 14th centimeters. Do you know how big that is? Well, I'll tell you how big that is. The radius of an atom, approximate average radius of a fairly, big atom, is about an angstrom, or 10 to the negative 10th meters, right? An angstrom, that's called sometimes. The nucleus of an atom is closer to 10 to the negative 15th meters. A that's a femtometer, right? So in order to draw the force of gravity to scale, I'd have to draw the vector smaller than an atom of ink. Can't do it. So the gravitational force is utterly insignificant as compared to the electric force, which is a really cool result. When we do these experiments and they're like dramatic and neat, you know, you can charge things up and they attract and repel really strongly, and they make awesome demonstrations the way it works. Really, really cool demonstrations. I really got to see if I can find some for you guys. The reason is because of that. Because, oops, I'm a little bit off screen there. Because how much more dramatically strong the electric force is. It causes really great, really cool effects. All right, long video, I'm sorry. Watch it on double speed. Sorry about that. But anyhow, good topic. Peace out.